Okay, so chain rule is such a cool rule that it gets its own little video here. And what the chain rule does is it tells us how to take the derivatives of nested functions, so functions that are functions of functions, and those come up more often than you might think. Okay, so let's say what the rule is and do a couple of examples. Okay, so the rule itself. So if we have z, which is a function of y, and y, which is a function of x, okay, then the derivative of z with respect to x is dz dy times dy dx. Okay, so the chain rule helps us work through functional relationships that have kind of steps in the logic, and that comes up a lot in social science. A thing about the chain rule, most people remember it in thinking about like kind of wrong thing. Yeah, didn't mean to erase. Most people remember it as thinking about differentials canceling. Okay, that's sort of what it looks like there, that you cancel the dy there and the dy there. And like that is fine as a mnemonic. It totally makes it totally easy to remember how things work. It's not really what's happening here. And it's good to keep that in mind. When I am writing dz dy, I'm not really writing like some fraction that has dz in the numerator and dy in the denominator. I'm using this whole symbol to denote the derivative of z with respect to y. And this whole symbol means the derivative of y with respect to x. There's no numerator and denominator necessarily in those derivatives. Okay. Just noting that, let's just go ahead and apply it. I want to show you sort of two different ways that we can apply the chain rule. One is in kind of like just math, finding derivatives type context, and the other is more of a social science modeling, let's sort out complicated relationships type context. Okay, so the first example, let's say we have this function. Z is 5x cubed plus 4x squared plus 1, that whole thing raised to the 6th power, and I want to take its derivative. How much do I want to multiply out 6 factors of that, and then take that derivative, or try to apply the product rule involving factors of 6? Not very much at all. I would really like to avoid doing that. I can avoid doing it if what I do is I recognize that we have nested functions here. We have a function here, and then we have that function raised to the power 6. So the way you may have learned this in the past, the way I learned it, and kind of a good slogan that goes with the chain rule is we have an inside function, which is the 5x cubed plus 4x squared plus 1. And we have an outside function. Okay, so to take that derivative and use the chain rule, let's just make that inside function, let's be explicit about what we think that is. So we're just gonna say, lurking in z, there is a function y, and I'm gonna let y equal that inside function. 5x cubed plus 4x squared plus 1, okay? And what that means is then z is y to the 6th power, right? I set it up so that y is the thing that we are raising to the power 6 here. And once I've got those things established, I can just say, okay, well, dy dx is 15x squared plus, running out of space here, 8x. And dz dx is 6 y to the 5th power. Chain rule says, let's just multiply those two things together. So that dz dx is dz dy times dy dx, that equals, so my dz dy is 6 y to the 5th power. it's right here, and my dy dx, that's my 15x squared plus 8x, all scrunched up over there. 15x squared plus 8x. And in one sense, I'm done, but I kind of want to go back and substitute out that y. And there's kind of two things motivating that. One is, for one thing, I just made up y to solve the problem. And so let's get rid of it for that reason. Another thing is that there's just kind of a convention. If you're taking a derivative with respect to x, the answer should be in terms of x as much as possible. So that is just 6. What is y? Remind myself what y was. It is the 5x cubed plus 4x squared plus 1 times 15x squared plus 8x. Okay, so this whole thing is my y, 6 times y to the 5th power. It will be the 5th power when I write it in there. So now that's right. This is my dz dy. This is my dy dx. And that whole thing is the derivative. Okay. You do this a lot. You'll get to a point where you don't need to write out what y is. You can just kind of do this step in your head. And again, that kind of inside-outside metaphor works. It's the derivative of the whole thing is the derivative of the outside times the derivative of the inside. You can see it the other way. I will say, writing out what y is when you're doing this chain rule sometimes can save time. It's really easy if you're taking a complicated derivative or just working through a long process to forget that derivative of the inside step. So writing it out sometimes actually saves you time. So, okay, so that's the example of the chain rule being used just in a kind of a pure math context. Here's a function that would be kind of ugly to take its derivative without using the chain rule. The chain rule makes it actually straightforward. So that's lovely. So second example is more of a kind of what we might think of as a formal theory type of example. And this would be about legislators induced preferences over procedures. Okay, so what am I talking about here? So if you follow like the legislative path of some kind of policy proposal, like the ACA or CARES Act or any of those things, and actually like kind of read the transcripts, what's talked about in committee, what's even reported in the kind of the DC press, CQ and things like that, a lot of the big fights can be kind of hard to even figure out what they're about because they're about kind of the details of administrative procedures, you know, which agency takes the lead, what kinds of evidence need to be used, how much lead time is needed, all of these things that isn't really clear what the stakes are and isn't really clear why we think legislators should be on one side or the other, okay? If we spin out a model of that, it's a model that has nested functions in it. So a model that you might think of is that preferences over procedures and how you do things come about by thinking about, well, how are those procedures going to lead to policy choices by an agency that's going to implement the law, and how do those policy choices affect groups? Okay, so that's a kind of a nested model there with several links in the mechanism there. So what that model would be saying in terms of math would be the preferences could be represented by utility function. Okay, so U is just a number that indicates it's high if the legislator likes what's happening and low if they don't like it. We have U be a function of W, where W is the welfare of some group. So if the first derivative of u with respect to w is positive, that's a group that the legislator wants to help, he's their friend. If it's negative, it's a group that the legislator is opposed to, he's their enemy. And the welfare of the group, we might say that's going to depend on the stringency of the policy. So is this going to be a policy that's going to make it easy to qualify for benefits or hard to qualify for benefits? That kind of thing. So again, this will be positive for some types of groups and policies and negative for others. And finally, the stringency of the policy depends on the openness of the procedures. I'm describing this at a pretty superficial level, like what does openness mean? Can we really array procedures that way? It'd be a lot of additional thought that you'd want to go through if you were really studying a policy proposal in this kind of framework. But the claim from this overall model is that the derivative of u, the derivative of the legislator's preferences with respect to the thing that we're actually arguing about, the procedures, that's going to depend on how the legislator feels about the groups whose welfare is affected, how the welfare of those groups is affected by the actual policy choice, the decision's probably going to be made by a bureaucratic agency, and how that decision is affected by policy. So this is what we would call induced preferences. Political scientists tend to think that legislators' preferences over these kinds of things are induced by their preferences over who they want to help, really. That the kind of the driving thing here is who's helped and who's hurt by the policy that's affected by the procedures. Not everybody would agree with it. It's a model that has its detractors. Some people would say no, that there's kind of intrinsic preferences over procedures. So this kind of argument could be used to sort out, this kind of model could be used to sort out an argument of if legislators' preferences are induced by the groups that are helped by the policy that's affected by the procedure, what would we expect to see under what kinds of circumstances? You could turn that into testable implications, look at it with data, and see if you actually have evidence that legislators' positions on these matters of legal procedure reflect their the nature of their most important constituencies, or are they actually, do legislators come in with, I really believe in easy access to the courts, those kinds of things, intrinsic preferences over procedures. Okay, so getting kind of far into the weeds of political science there, the point I was just trying to make here is that we can use the chain rule without any specific functions just to help ourselves organize complicated relationships in a model. Okay. So the chain rule is great, very empowering. We've got one more video on basic derivatives, and I'll see you then.